Good evening, everyone. This is our second day of Faculty Development Program. This FDP is organized by Department of Electrical and Electronic Engineering of Studiwell College of Engineering. This is an AICTE ATEL FTP sponsored development program. So our resource person for this session is Dr. Isaac Josho Ramesh Lalwani, who hold BE and ME in Mechanical Engineering and a PhD in Renewable Energy and Automobile Engineering, and is Associate Professor at Advanced Institute of Technology, Ethiopia. His expertise includes automobile engineering, renewable energy, alternative fuels, and electrical vehicles, and he has more than 50 publications with an H index of 21. Sir, we welcome you to the session.
Yeah, thank you. Just I welcome all one for this session on smart energy management system for low carbon cities. I hope you can see my slides.
Yes, sir,
Am
it's
I right?
visible. Yes, sir, it's visible.
Yeah. Let us go about some small introduction. Smart energy management systems are essential for developing low carbon cities that aims mainly to reduce the greenhouse gas emissions. Okay, and meanwhile, we are just maintaining the urban growth and quality of life. This system always integrate advanced technologies and data analytics and renewable energy to just optimize what we are getting from them. And again, it will be just helpful to maintain our environment. So this advanced smart energy system not only just reducing the consumption or optimizing the data technologies by means of input, it is also has to be supposed to incorporate renewable energies. Okay. So here, what are the main components of this your smart energy management system? You can see the first one, it is smart grids. The second one, advanced metering infrastructures. The third one, distributed energy resources. And the next one will be building energy management systems. And the next one will be the data analytics and artificial intelligence. The next one, integration with urban mobility. These are the major components of smart energy management systems. Here, this is the animation of this smart grids. Let us discuss about this smart grids. The smart grids is an advanced electrical grid system that incorporates digital communication technology to provide two-way information flow. It will have both end user side and also the supplier side. Its flow between the suppliers and the consumers. It integrates advanced latest intelligent devices, smart meters, sensors, and control system. It improves the efficiency, reliability, security, and the most pronounced sustainability of electrical generation, distribution, and consumption. So here you can see it enables the real-time energy flow monitoring and automated control integrating renewable energy sources such as solar, wind, or tidal. Here it allows for dynamic pricing, demand response, and grid reliability. So only we are telling it is a two-way system. Okay. So what are the core features of smart grids? Okay. Here you can see the list of core features of the smart grids. Okay. Here, the first one here, the smart grid use sensors, meters, and communication devices in the real-time energy flow monitoring and automation control. Here, the automated controls respond to fluctuation in supply and demand and optimizing energy flow, and it reduces the wastage. The second one, the integration of renewable energy resources. Here, the smart grids can smoothly incorporate the renewable sources. Majorly, it will be a solar and wind, okay, which are variable in the output. So by balancing these sources with traditional generation and storage, smart grid supports the transition to low carbon energy systems. The next one, dynamic pricing and demand response. Here, the advanced metering infrastructure, it enables utilities to offer dynamic electricity pricing based upon real-time conditions. Consumer can also adjust their usage in response to the price signals, aiding grid stability, and often it is helpful for himself by saving the money. Here, the demand response programs allows utilities to incentivize customers to reduce or shift their energy usage during their peak demand periods. The next one, the grid reliability improvements. Here, with intelligent fault detection, self-healing capabilities, and predictive analysis, smart grids help minimizing outages, quickly isolate problems, and maintain consistent energy delivery, even as distributed and renewable sources grow. So here, the next one, we'll be seeing about it, what will be impact on the low carbon cities, the smart grid. By enabling the efficient integration of renewables, flexible demand management, and reduced losses, smart grids are crucial in building sustainable, resilient urban energy system. And again, technologies like automated controls and real-time monitoring position cities to lead the global shift towards the cleaner energy and reduced carbon emissions. So here you can see the modern smart grid system. Here you will be having the different parts. Okay, you can see the solid arrows. It represents the energy transfer between the generation, storage, and the end users. And the dashed arrows, it represents the information flow enabling the communication system between the sensors and again the EMS and again grid operators for real-time monitoring, decision making, and automation. So basically, you can see this modern smart grid system. It has energy sources. The energy sources, what we call is like renewables, solar panels and wind turbines generate energy, which is fed into the grid. Next one, you will be having a backup generators. Here you can see it provide additional power when renewable sources are insufficient, okay, to meet the demand. And again, on-site energy storage, it stores excess energy for later use, helping balancing supply and demand. And again, EMS, energy management system, it is basically a central control unit that manages power flows, monitor grid conditions, and decides when to use renewable energy storage or backup generations. It just receives information about power availability and controls how energy is distributed. Okay, and information the EMS uses the real-time information, real-time data analytics dashboards to make operational decision on how to operate the system on the particular demand condition. Next one, the demand side management policies and possible trades. Basically, it is given as DSM policies. So here you can see that it is a strategy to regulate or influence energy consumption pattern. For example, shifting usage to the off-peak times. When there is no peak hours, you can just shift the usage. Okay. So this up to this, you can see about the modern smart grid system. The next one, in the case of the core features of this low carbon systems, you can next see the advanced metering infrastructure. Here, the advanced metering infrastructure, you can see it is a cornerstone of modern smart grid technology. It refers to integrated system that enables two-way communication. Okay, it is all getting the data and again correcting the whatever the supply we are giving. Okay, it is a two-way communication between the utility providers and customers by means of advanced metering, communication networks, and data management. Okay, the features, the main features, we will be having a two-way communication. What two-way communication already we had discussed. It's a real-time data transfer between utilities and the end users. It enabling utilities to monitor the electricity usage and instantly, and they can respond remotely. The next component features will be a smart meters. These digital meters records energy consumption in intervals, maybe often hourly or less than hour also. And it communicates this data to both utilities and customers, supporting more detailed billing, dynamic pricing, and demand response. The next one will be the communication networks. It is the basic backbone of this advanced metering infrastructure. It enabling reliable and secure transmission of data. Okay, networks can be wired or it may be wireless. Okay, it's based upon the system what they are using. The next one, the data management system. Here, it just AMI, okay, advanced metering infrastructure, collects, stores, and process large quantities of usage data. And utilities analyze this data for operational efficiency and again outage detection, and also to provide the customers with actionable usage insights. Okay, so here let's see about the remote operations. So here, this utilities can remotely connect or disconnect service, and again it detect or pinpoint outages and identify the issues like energy theft more efficiently. Okay, that is the main just feature of this remote operation. And again, support demand response by enabling the real-time monitoring and customer engagement. Advanced metering infrastructures just facilitates demand side management programs, helping to balance the grid load and prevent outages during the peak period. So here you can see the next slide. You can see the importance in the case of smart grids, this AMI. It enhances the efficiency, reliability, and sustainability of electricity delivery. It empowers just consumer with information and control and helps utilities optimize operations, integrate renewable energy source, and improve customer service. Okay, so it is just play a crucial role in the modernization of the grid. Okay, so here you can see the picture which shows the basic structure and data flow of the MI system in a smart grid context. Okay, here you can see first how this system works. You can see the first one. It is a single family home with a single smart meter. Okay, here the electricity usage is measured continuously by a smart meter installed at a home. Instead of traditional monthly readings, this smart meter collects and sends detailed real-time or just near real-time consumption data. Okay, and here you can see the communication devices. Okay, on the tower you can see here the smart meters wirelessly transmits the data to the nearby communication device, often located on a utility power. This device aggregates the usage information from many homes in the area, and it acts as a relay point. Okay, and again the utility office where you will be just sending the just supply to all the places. Here, the collected data is securely transmitted from the communication device to the utility company, whether it is a governmental or it is a private. Okay, here it will be acts as a data center. Here, the data is processed, analyzed, and it is used for accurate and timely building and outage reduction and restoration and demand response programs and just giving consumer insights into their consumption patterns. Okay, it will be helpful for this one. Okay, so the next one, your distributed energy resources. Okay, this distributed energy resources, you can see it is a small scale energy generation, storage, and controllable load technologies. Okay, they are just located close to the point of energy consumption like homes or business rather than centralized power plant. Okay, it is a distributed energy resources. Okay, not it is like a just a centralized power plant here, so that the load flexibility everything can be managed simply. It's contributed to more flexible, resilient, and sustainable energy system by enabling local energy production and management. It helps to reduce just relying on large power plants and supporting just integration of renewable energy resources. Okay, here you can see what are the examples of this renewable energy resources or just power systems what we can use here. So your PV panels and again your wind turbines, battery storage system, EVs, combined heat power systems, small scale hydropower, fuel cell, diesel or natural gas power generators, demand response technologies. These things, microgrids, these are the things which will be used as a to just make the power decentralized, and it can be just done by means of the different areas, not like the centralized part. Here you can see the example or the just the typical power distribution system moving from electrical generation stations to the transmission lines, substations, and distribution transform until they reaches the home services. Okay, so this is the DER system. You can see it includes solar panels, wind turbines, batteries, and other technologies locally rather than centrally. You can see the infrastructure also includes important components like safety and functionality like ground rods and electrical meters. You can see on the right side, The house is also equipped with renewable energy sources like solar panels, wind turbines, representing the integration of DRs alongside traditional power infrastructure. They allow buildings to generate, store, sometimes even sell electricity when the demand is more, just increasing the grid flexibility and just resilience. Okay, so next one is building energy management system. Here, it is a technology, a platform for real-time monitoring and control the particular building energy storage. It combines sensors, meters, controllers for comprehensive data collection. It tracks energy consumption, temperature, lighting, and environmental factors. It enables intelligent control of systems like HVAC and lighting. Okay. Here it improves the energy efficiency and reduces the operational cost for the particular building. So here you can see the enhanced energy efficiency by means of smart managers. It also declines overall energy cost by optimizing the utilization. It maintains the occupant comfort with precise environmental control. It supports sustainable goals by minimizing the energy wastage. It utilizes automation for continuous system adjustment by means of getting the data from the operational data centers. It leverages data-driven, optimized, and informed decision making. So they have programmed for managing this energy. So here you can see the example which summarizes the architecture of the building energy management system. It shows how various building components such as HVAC and critical utilities, lighting, process equipment, and energy management systems are connected through dedicated controllers to central battery energy management system network. Data from this system, as well as submitters for energy, water, and gas, are collected and sent securely to the cloud platform for analysis. There, it enables engineers and automated platforms to monitor and optimize and control the building energy usage effectively so that it can be managed effectively. So the next one, data analytics and artificial intelligence. Okay, here it just you can see this data analytics and artificial. Here it transforms the energy management by processing the very large quantity of data volumes from sensors and meters. Okay, it generates the insights to make the betterment in the energy performance. Okay, it enables the on-site real-time monitoring of the building management system, and it provides predictive forecasting of energy demand for proactive management. Okay, so the data analytics and artificial intelligence will be used for this. Okay, it detects any anomalies to prevent energy waste and system failures. It supports optimal resources allocation to enhance efficiency. It reduces the waste and it lowers the operational costs. It enhances the occupant comfort through intelligent system adjustment. It facilitates better integration of renewable energy resources. Here you can see the applications. This image summarizes the role of data and this AI in building energy management. Okay, it shows how building system connects via open protocols to monitor the energy consumption across gas, electricity, water, and renewable sources. So here the data is securely communicated to the energy application servers, where advanced analytics are used to analyze the energy cost and generate carbon reports and detect abnormal energy use for improved efficiency and sustainability. So this is how your data analytics and AI will be useful for us. The next one, the integration with the urban mobility. Here, this integration with urban mobility, particularly you can see EVs. Okay, it is shaping the future of energy efficient cities. Okay, smart grids enhance energy distribution and support renewable integration, while e-mobility reduces the emissions and also the noise pollution. Together, they enable load balancing by scheduling EV charging during off-peak hours and using P2G technology to allow EV to return the stored energy to the grid, improving the stability of the grid and energy. You can see the cities like Amsterdam, Singapore, Oslo are pioneering this integration. It will be shown the proven low energy consumption and reduced carbon footprints and healthier urban environments through by means of improving the better air quality and quieter streets. Okay, so here you can see how the integration of this urban mobility will be helpful. Here, this image highlights the smart grid as a central technology that connects various sources, okay, and consumers of electricity. It enabling efficient energy management in the case of cities and urban areas. You can see the power generation. It includes both conventional thermal power plant and nuclear power plant, hydro power plant, and also the renewable sources like solar and wind power plant. Okay, you can see the urban and industrial loads. Here you can see the feature building cities, factories, smart homes representing the different types of consumers who are all available in the case of the particular place. And again, electric vehicles, it showcases the integration of transportation into grid, which is the example of urban mobility. So, urban mobility it refers to the use of EV and connected infrastructure to create a seamless, sustainable, and efficient transportation system powered by the smart grid. So, the smart grids enables dynamic energy sharing, supporting charging stations, and manages the power flows between vehicles, buildings, and renewables. Okay, so this basically how smart grids coordinate diverse power sources and urban infrastructure and advanced energy efficiency, and how it supports the cleaner, smarter urban mobility solutions as we showed in this figure. Okay, so now we will be discussing about your EV. So electric vehicles, they are automobiles powered by one or more electric motors, which just uses the electricity as the primary source of energy. Okay, they operate without traditional ICGs, and also it also get the supports of ICGs also in the case of hybrid vehicles. Okay, so you can see the EVs use rechargeable batteries, store and provide electricity for propulsion. With the rise of climate change and increasing concerns about air pollution, here this EV offers a sustainable alternative to provide a traditional fuel-powered cars around the world. So here the electric vehicle uses the rechargeable batteries. Okay, so this rechargeable batteries will be just helpful to produce zero emissions, making them very environmental friendly. Okay, and again, EV offers a cheaper running cost as a smoother, quieter ride also, with the benefit of instant torque and acceleration, unless like your ICE engines with the gearbox to just have more torque and lesser speed in the first gear. Then to increase the speed, you are going for the second gear, third gear, so that your torque will be reduced and your speed will be increased. It doesn't act like that. It just have the instant energy. Okay, the pickup or the experience of this vehicle will be very sophisticated and highly efficient. Okay, so you can see the history of electric cars. Okay, you can see it has just broken into six distinct periods: 1830 to 1880. Here, the just earlier pioneers of electric mobility happened. Okay, then 1880 to 1940, the transmission to just motorized transport, and 1940 to 1970, the rise of ice engines and the oil crisis, and again the climate concerns were be growing about the emissions. Okay, so again 1930 to 2003, the electricity vehicles just returned, and we are considering 2003 to 2020, we are calling it as the electric revolution, and by 2021 to the present day, it is like the tipping point and beyond the two. So this is how your EV vehicles beyond. So now we will see when the first electric car. Okay, the US, the first practical electric car was built by means of William Morrison, a chemist. Okay, surprisingly, he's a chemist, and Morrison's vehicle was a traditional horse-drawn Surrey carriage. Okay, and in 19th century, America, which was converted to fit a battery in the Morrison's electric carriage, and it could carry a maximum of 12 people. Okay, and had a maximum speed of 32 kilometers per hour. Okay, so that will be a milestone in the case of. So here you can see the how the electric vehicles, and what are the key components of it. It always have a traction battery pack which stores electric energy and it used to power the vehicle. Okay, and again it has an electric traction motor. It converts electrical energy into mechanical energy to move the electric. And again, it has always has a power electronics control. It manages the flow of electricity to the motor and other components. It has an onboard charger and it has a charging port. It allows the EV to be plugged in and charged from an external source. And again, a thermal system, cooling is must. It maintains the temperature of the battery to work it efficiently and electronics and safety. Okay. So the next one, you can see the types of EVs. Okay. Battery electric vehicle. Okay. It will be called as battery electric vehicle. It has a battery packs and electric motor. That's it. Next one will be the hybrid electric vehicle. It has a fuel tank, it has a battery, it has a conventional internal combustion engine, and it has an electric motor also. Here, the next one will be called as a PHEV, plug-in hybrid electric vehicle. Here you can see it has a fuel tank, it has a battery, it has a IC engine, and the electric motor. The last one will be the PCEV, fuel cell electric vehicle. Here it has a hydrogen tank, okay, which has a fuel cells, which has the ability to just produce the electricity online. And again, it has a battery, and again, it has a electric motor. Okay, so the first one, the electric battery electric vehicle. Okay, it is a simple component. It has just run by means of stored electricity in the batteries, and just it can be recharged by means of external source. They are emissions free, efficient, and eco-friendly. It is just making the better environmental friendly to reduce the carbon. Okay, you have already Tesla Model S, Nissan Leaf, and Renault Zoe, which will be coming under this battery. So the advantage, what are the pros? Zero emissions. It is cost effective. It can be quickly escalate, and you can see the government will be giving many incentives to buy the battery electric vehicles, and it will be promoting the policies to improve the just the reducing the emissions by means of battery electric vehicles. So, what is the problem or disadvantage which concerns about this battery electric vehicle or pure electric vehicle? So here the range anxiety. Recently also we are just hearing about many cases of this non-availability of charging port, and in the midway the vehicle has been stopped like that and the support has been called for like that. The range anxiety, the biggest issue in the case of this one. And again the charging infrastructure. Okay, how much like conventional fueling station, how much charging ports are available. Okay, and the charging time is more. The refueling time is almost you cannot compare with the conventional fueling system where you can fill in some minutes, whereas this charging will be taking a lot of hours. Okay, and again due to the expensive battery, your cost upfront cost is very high, which just people are hesitating to buy this cars. Plug-in hybrid electric vehicle. Here it just combines fully electric and traditional vehicle. Okay, whenever the vehicle needs to start, it uses the IC engines where it needs more torque. While it's running at the cruising speed, the average speed, at that time, it will be used the electricity motor so that even the power consumption for this electricity motor will be less for the cruising speed. It operates on just electricity, but it can switch to the IC engines also when the battery is low. And batteries can be also recharged from the external power source. Already the available products will be Toyota Brace, Prime, Chevrolet Volt, and Mitsubishi Outlander. Okay, so here the advantage, the versatile fueling, it able to just extend the range by means of conventional fuel. Okay, it lowers emissions compared to the fully operated ICE vehicles. And again, here also government will be giving possible tax credits and rebates. Okay, so what is the concerning points in the case of disadvantage in this case of the system? Here, it has more complicated parts compared to the simple electric vehicle or simple IC engines. This combining of this IC engines and also this your hybrid system will be making the system more complicated so that you cannot simply maintain or just look into the system very simple. And again, you can see the electricity range will be limited to 20 to 40 miles on electric power alone. Okay, so it is less efficient on fuel. It reduces the efficiency when operating on the fuel. Okay, petrol or diesel. Okay, so the next one will be the hybrid electric vehicle. It combines your IC engines with the electric power system. Here it's charged by engine, and here the advantage is it has a regenerative braking. So while the vehicle is running and it will be just using the braking or something, it uses that frictional mechanical energy to charge the battery so that the charging will be done while the vehicle will be operating also, so that it improves the fuel economy and it reduces the emissions, okay, compared to the conventional vehicles. The present system will be the Toyota Prius, Mazda 2 Hybrid, and Toyota Yaris Cross. Okay, so here the advantages, the fuel efficiency will be just more compared to the previous vehicles, and it has a reduced emissions and no need for any external charging. It itself will charge inside the same system. Okay. So the disadvantages, limited electric power. So here again it is like minimum electric only, just used for operation. And again it has higher cost compared to the conventional fuel vehicle. And if the battery is failed, the battery replacement cost is very expensive. Okay, and again, even the life cycle of the battery is more. The battery's cost will be very high. So the next one will be the fuel cell electric vehicle. It will be just the system which uses the hydrogen gas, which is converted towards electricity by means of the fuel cell to just power the motor. It's like a battery. The fuel cell will wax from power from cathode to anode like that. It just releases only a water vapor. Your external output of this hydrogen process comparing to the electricity. The outlet will be the water vapor, and it provides generally electricity in the onboard just immediately, so that it has a longer range, and you can see it is comparatively, you can call it as faster refueling than the battery electric. You can just change the hydrogen gas cylinders within a short duration, not like charging it more hours in the case of your normal battery electric vehicle. The examples will be the Hyundai Nexo, Toyota Mirai, like that. Okay, so here you can see the advantages. It is efficient and clean. It's quick refilling. Comparably, it is very suitable for long distance. The problem is infrastructure issues. Few hydrogen refueling stations will be available compared towards your charging ports. Here, it has a high vehicle and fuel cost. The technology and the hydrogens are very costlier compared to the other electric power cars and this ICE these vehicles. And hydrogen production is not always green, okay, because we have a different kinds of hydrogen, gray hydrogen, and again turquoise hydrogen like that. Only the green hydrogen, which is produced by means of this renewable system, will be called as your green hydrogen, or else you cannot call it as totally environmental free, because while you just analyze wheel to wheel analysis, the your emissions will be more. You cannot tell it as totally emission free, because the hydrogen production process may needs some emission process which will be increasing the emission and also increases the cost. Okay, so here we see compare the hydrogen fuel cell vehicles and these. Both technologies have distinct advantages and challenges. Okay, suited to different needs and infrastructure based upon the particular city or particular country where you are living. It decides what vehicles you can use. Still, there are cities are available in our country where you cannot have a system of using the electricity vehicle. Okay, your electricity vehicle you cannot operate in the case of the system, and hydrogen. Still, most of the places you cannot use this hydrogen fuel cell vehicles. Okay, So you can see just a simple comparison, the different aspects of this hydrogen fuel cell vehicle and battery electric vehicles. Here, the energy source will be hydrogen gas, where it is electricity. Here, the emission is simply the water vapor, and again, here it is a zero emission if it is charged from renewable energy source. You are just charging by means of a diesel power generator or fuel power generators, then it cannot be called as a zero emissions because wheel to wheel analysis will justify it as a emission. Okay, so the refueling and charging time. Here you can see the hydrogen gas can be refilled by 3 to 5 minutes, whereas you can charge it minimum of 30 minutes to just go to several hours, depending upon the charger time. The range will be just 300 to 400 miles in the case of your hydrogen fuel, whereas it is 150 to 300, moderate compared towards your hydrogen. Okay, the efficiency is lower because of the energy loss which is happening during the hydrogen production, whereas here it is having a higher efficiency because of directly electricity is used. Okay, so the infrastructure, the limited hydrogen refueling stations, whereas the electricity is well developed now, and the more charging networks are globally evolving. So we can just have well developed infrastructure in the electricity. Okay, and again the cost, you can see it is very high in the case of the hydrogen fuel cell vehicles, whereas the battery electric vehicle, it is just compared to your HFCV, it will be just cheap. Okay, and again the technology, it is emerging in the case of hydrogen fuel. Electricity technology or electric vehicle technology is already established and is widely adapted. Okay. If you see, depending upon the type of hydrogen production method used, it may be it will be creating a disadvantage to the environment, or it may be just reducing the emission. And again, battery electricity vehicles, it is minimal if charged with renewable energy, as we discussed earlier. So you can see it will be hydrogen fuel cell vehicles is ideal for very long distance travels and commercial fleets, whereas your battery electric vehicle will be used for urban transports and personal use only. So now we can see the importance of EVs and hydrogen fuel cell vehicles in the case of your energy transition. So here you can see the electric vehicle system and hydrogen fuel cell vehicles. They are critical in reducing the global greenhouse gas emissions and achieves the sustainable transportation focus on transition from fossil fuels towards your renewable energy. So why these vehicles are important? It reduces how it will be used for this reducing the carbon footprints. It reduces the greenhouse gas emissions. It enhances energy security and reduces reliance on fossil fuels. It promotes technological innovation and supports global climate goals and economic benefits and also the local job creation. So here you can see this graph how shows it shows the global EV adoption rate globally from 2020 to 2026. Here, the x-axis represents the years and the y-axis you can see it shows the percentage of EV market share. You can see the EV market share starts at about 1.5% in 2020 and it rises steadily each year. By 2022, it reached approximately 3.5%, and you can see by 2024 it becomes 6%. And you can see the projection for 2026 is 10%, it indicating the rapid growth in the case of your market share of your EV vehicle. Okay, so here we can see the environmental benefits of this EVs. It has zero tailpipe emissions, it reduces the air pollution, significant reduction in greenhouse gas emissions, lower carbon footprint compared to your conventional ICE vehicles, so that it supports the sustainable urban development. Okay, so next, the role of this EV in global energy transition. You can see decarbonization of the transportation sector, integrating with renewable energy sources. It reduces dependency on fossil fuels and promote energy efficiency and innovation. So you can see just compare the Indian scenario versus global perspective in the case of this EV. So here also India, we will have the FAME 2, which is the faster adoption and manufacturing of electric vehicle. It provides subsidies for EV purchase and development of charging infrastructure. And again, it is also having some PLI schemes which boost domestic battery manufacturing. And again, it just encourages the new startups to just produces the different battery and EV related batteries. So here, the government policy aims target of 30% of EV penetration in private cars and 70% for commercial vehicles and 80% for two and three wheelers by 2000. So, sorry. You can see the challenges. Okay, here the challenges what we have is inadequate charging infrastructure, high initial cost, and dependence on imports for the lithium-ion batteries. And again, it has limited consumer awareness. People are not agreeing with this EV system because they don't want to change it from the conventional, well-known system of ICE. So, in the global perspective, the EV market will be just dominated strongly by means of China. Okay, particularly, they are a strong battery supply chain, and government incentives also more. And you can see the Europe has aggressive emission regulations and high EV adoption. And again, United States, its growth in the EV adoption due to the federal instincts and Tesla's are the home place of Tesla's years, and they are market leaders there. So the global challenges, what is in the case of EVs? The first one, high purchase cost, charging infrastructure, ranging circuit, grid capacity and energy sources, limited model availability, and again, regularity and market balance. Battery life cycle concerns, and again, consumer awareness and perceptions, and limited raw material for the batteries available throughout the world, particularly T1 code. And again, the most important concern, even we are telling it's emission free, how you are going to just recycle and dispose this batteries is a major concern and a global challenge. So here you can see the insights of this global perspective in the case of EVs. Here the EV sales exceeded around 20 million units in 2025, just comprising 25% of the new cars will be the EV cars. And the total global EV fleet reached nearly 58 million cars by end of 2024. And China leads with nearly two-thirds of global EV sales, followed by Europe and US, okay, by like 17% and 7%. And again, emerging markets in Southeast Asia, Latin America, and Africa, just showing the rapid growth in EV adoption. Over 785 EV models available in 2004, and again, it is forecast to reach 1,000 models by 2006. We have very more options of this EV models. And battery technology advancement just improving the charging speed and range and affordability. So EV accounts for about 43% of global vehicle sales, up from 9% in 2010. Okay, so from 9% to 43%, just reflecting the rapid market share. Okay, so here you can see the comparative analysis India versus global. So EV adoption, emerging market 2 to 3% penetration, whereas the global just leaders it has greater than 20%. So battery supply chain heavily reliant on imports, particularly from China, whereas the global leaders they are having a very good integrated supply chains. And again, the infrastructure, limited charging and refilling points still not, whereas the other place, the global leaders have well-developed just key regions. Okay, so the global innovations in the EV. So what are the things which will be supporting the EVs by means of innovation technology? First one, smart charging infrastructure and vehicle to grid technology. And again, AI and Internet of Things in EV management system. And again, lightweight battery design. And again, integration of renewable energy with EV infrastructure. And next one will be the breakthroughs in the EV motors and controls. So here you can see the smart charging infrastructure. You can see what are the things available. So EV charging station management. Okay. So here you can see smart infrastructure manages the EV charging stations by means of automation control, scheduling, and monitoring of charging activities to maximize the efficiency and convenience. Okay, so the next one you can see the communication between EV charger and vehicle. Okay, here there is a real-time two-way communication between the charger and the vehicle, just enabling dynamic exchange of charging status, battery levels, and charging needs. Okay. Next one, the load balancing and power management. Here, smart systems balance the electrical load across multiple chargers, optimizing the energy distribution and preventing overload in the power grid using advanced power management techniques. The data analytics and report. So here, the continuous data collection from the charging operations just enables, okay, it enables the analytics and reporting for performance optimization and also the predictive maintenance and consumer insights. Okay, what's happening inside the vehicle. So these features collectively make smart charging infrastructure more efficient, scalable, and responsive to both user and also the grid needs. Okay. So the next one, you can see the just the features. Okay. Here you can see just features of this smart grid infrastructure. It's listed. First one is dynamic load management based upon the needs, and again integration with renewable energy. Cost optimization based upon time of use pricing, and again, what are the benefits you can see? It reduces the strain of heavy load in the case of the grid, and it enhances the user experience and it promotes the energy efficiency. So the next one, you can see the vehicle to grid technology, advanced technology where your vehicle supplies the power towards the grid when the demand in the grid will be more, so that your whatever the energy you are supplying to the grid will be metered and you will be given rewards for it. Okay. So the vehicle to grid technology, it enables bidirectional energy flow between, you can see, EVs and the power grid. It allowing EV batteries to both just get electricity from and also to supply the energy back towards the grid. Okay, it's a two-way process. It can get both the input power and also it can send the supply towards the grid. Okay, so just it is a two-way thing. Not only getting the power from, it also send back power. So what are the components you can available is first you will be having a V2G enabled vehicle. Okay, you have to have a vehicle. All vehicles cannot be just used for this process. You have to have a enabled V2G vehicle. Here the electric vehicle just equipped to support two-way energy transfer, whether as input and also the output. And again, it has a bidirectional EV charge. It allows energy to flow both into the vehicle for charging and also it has to send out the energy out of vehicle for the grid supply. And again, you need a power grid and a household. Here, the vehicles can feed power to a home or directly to the grid, helping to manage local electricity demand and supply, particularly in the case of e-commerce. And again, you may also have a solar inverter. It is an optional one. Okay, for if you have solar panels that can generate DC power and converted by an inverter towards AC power, alternate current, which can be used in the home grid or it can be stored in the EV. So during how the process happens during the time of lower electricity demand or high renewable generation, EVs can be charged using excess grid or solar power. When the demand is high, stored energy in the EV can be just sent back via the charger to power the house or supply the grid. so that it supports grid stability, and also it will be having a energy savings also. So now you see the benefits of this V2G. First one is grid support. It balances supply and demand. It mitigates peak load and supports grid resilience. And again, cost savings. House owners can be used cheaper off-peak electricity to charge EVs and discharge during the expensive peak times. Okay, based in some countries, it has a system of dynamic pricing. Okay, when you are using the electricity in the peak hours, the price of the electricity will be more. Okay, your systems will be calculating the price based upon the which time you are using the electricity. And again, the integration with the renewables. It facilitates better use and storage of solar energy, smoothing out generations fluctuations. Okay, so that it will be very helpful to just maintain the power supply without the fluctuations. Okay, so here you can see B2G can design leaf. Okay, you can have only you can have some, not all the EVs currently supporting this bi-directional cable. Here you can see the Nissan Leaf E1, and again you have a Nissan END200, and again you have Mitsubishi Outlander, Mitsubishi Eclipse, plug-in hybrids. Okay, while these vehicles have been available for 7 years, the technology is still in the trial phase in the most. We are in, it is not well established system. Okay, like your ordinary electric vehicle vehicles. Okay, so next one is AI and EV management system. Okay, here basically it will be used for the battery management, autonomous driving, energy optimization, and maintenance. So the AI technology will be used for these things in the case of. So the battery management, it's just it predicts chances for battery. All systems of the EVs continuously, so that it will be giving the alert about the failure of the system, so that you can just avoid the breakdown of the vehicle. Okay. So the IoT in the case of your EV management, Internet of Things. You can see the image. It shows how IoT integrates with EV management system to optimize the charging, monitoring, and user interaction throughout the EV ecosystem. Okay, here you can see the transmission grid to charging. Okay, you can see here transmission grid to charging. You can see in the above. And again, you will be having a EV charging, and you can have IoT and communication flow, and you have a data processing and user interaction, and you have a smart services and payments. Here, transmission grid to charging. Here, electricity generated and transmitted by the grid or renewable sources, maybe solar or wind, is stored, processed, and balanced within lithium-ion battery cells before being used for EV charging. Okay, to be stored, processed, and balanced. Okay, in the battery cells. Okay, in the case of your transmission grid to charge. And again, in the case of EV charging, the processed energy is delivered to EVs via charging stations. These stations and vehicles are IoT connected for real-time data exchange. You can see the IoT and communication flow. In the case of IoT gateway, all these devices communicate with the centralized IoT gateway. Okay, you can see the hub icon or home icon in the case of the image. It facilitates seamless connectivity to the internet. Okay, and again, the case of data processing and user interaction, Here, the cloud data processing, which collects the real-time data from EVs and charging infrastructure, is uploaded towards the cloud servers for processing and analytics. So the process data is accessible over the internet. Okay. So by means of mobile app integration, users access information about charging location, status, and again the billing exact. Okay. It will be having a dedicated mobile app, and this app facilitates the remote control and monitoring of the vehicle and charging sessions. Okay, it will be having the whole data. So in the case of smart services and payment, you can just you can see the charging location service. The system helps to locate available charging stations using real-time data transmitted through the IoT network. And again, it also facilitates the banking and payment. Okay. So here the app integrates with the banking system for seamless, secure payments. And when users initiate or complete just charging sessions, okay, it will be giving the notifications about it. Okay. Next one, applications. Okay, here you can see smart charging, fleet management, remote monitoring, and connected ecosystem. These are where IoT will be just integrated in the case of EV management system. The case of smart charging, integration with the grids for optional charging, and again the case of fleet management, real-time tracking and diagnosis for the EV fleets. Okay, where it is located, what is the state of battery charge, when to maintain the particular vehicle, all will be given in the case of the fleet management software. And again, you can just continuously monitor the health of the EVs, and also you can just monitor where the vehicle will be available within the working range. It's the case of it will be having integration with the smart homes and cities so that it will be connected ecosystems. So what is the benefit of integration of IoT and AI? Okay. So here you can see it has enhanced user experience with real-time data, seamless communication between EVs and infrastructure, and predictive insights for grid balancing and resource optimization. And it facilitates autonomous and smart mobility solutions. Okay. So you can see the global innovations and examples in the case of your AI and IoT synergies in the EVs. Okay. You can see Tesla, Nissan, BMW, and China's smart EV cities. These are all will be having the global innovations, and they are market leaders. You can see the Tesla AI-driven battery optimization and autonomous system is there in Tesla. The case of Nissan, you have IoT-based remote control through Nissan connected app. Okay, the separate app, you'll be having all remote controlled operations of this Nissan vehicles. And again, BMW, AI-powered predictive maintenance systems are there. And in the case of China's smart EV cities, IoT-enabled urban EV ecosystems will be there, which is helpful for more things. So, your smart grid vehicle technology will be used totally with the help of your AI and IoT systems. So, what are the challenges? Okay, it will be there in the case of this AI and IoT. Most of the things of this advanced system, you don't have data privacy. It is always used to just accept its terms and conditions. It doesn't have any option to reject the terms and conditions. It always monitors the data privacy and cyber security. And again, the system development cost. To develop the system, the cost will be more. And it needs robust infrastructure, particularly the countries like India. We have a very high population, which restricts us to have a robust infrastructure. Okay. So, what are the solutions for this challenges? Strong regulation and standards must be provided by the government policies. And again, the institutional investors have to invest in the research and development of this new kind of systems, particularly the development of AI and IoT system, which is can be just programmed or coded by the local country or home country. And again, public and private partnerships for the infrastructure too, because government cannot develop the full structures because it has a problem with funding and other systems. So it has to just combine with the private things so that it can be developed, like how Tesla and US government is doing. So here, in the case of EVs, light materials, this is the another innovation that will be needed. And so you can see our old ambassador vehicle and old Fiat vehicles, which is how heavy the vehicle is there. Now we can see our present ICE vehicle, that is, I can tell it as our Maruti Suzuki Swift Desire, which has somewhat very lighter outer body panels compared to our previous ambassador. Even if you push little hard, it will be having a dent. So why it is made it like this? Okay, why ambassador car is just an ambassador kind of cars which is having a very hard sheets, which will be just modified now towards a present car. Compared to ambassador, all our present cars will be having a very light sheet. Why it came towards light materials? The first thing, the major priority, the case of lightweight materials, even in the ICE vehicles, it is the first priority is because of the fuel consumption. The vehicle's curb weight will be totally reduced so that your curb weight of the vehicle will be reduced so that you will be having a better. The most another thing is like safety. The vehicle has to absorb the energy and it has to disperse. Okay. And that will be done only by means of the couple. So the bonnet area in the front and back side, which is designed to just crush and absorb the energy during the accidents. So it is made up of the lightweight materials. So that it will be just broke and it will be just absorb the energy so that the impact of the accident will not be absorbed by the people. The case of EVs, it's not because of the safety or other reasons. To increase the battery life, if you are having more lightweight materials, it will increases the running hours and it also increase the SOC of the battery while the vehicle will be running. So that is the why we need lightweight materials in the EVs. Here you can see reduced vehicle range improves the energy efficiency. It enhances the battery range and reduces charging. And again, it supports the structural safety and performance and contributes to the overall sustainability. So, what are the materials which is helpful in this goal optimization in the case of innovations? Aluminum, which is lightweight, and again, it is corrosion resistance. And again, the next one is carbon.
So voice is not audible, sir.
Yeah, ma'am, I had a power interruption.
Okay, okay, sir.
Okay, okay. Now is that visible?
Yes, sir. Now it's audible, sir.
You can see the PPT or not?
Its voice is breaking, sir. Actually.
Okay. Whether the PPT is visible, man.
Yes, sir. Now it's not visible, sir.
Okay, okay. Let check. Okay.
1 second before till that visible. Now it's not visible.
Wait a minute. Wait a minute. I will.
No problem, sir.
I hope now it's visible, huh?
Yes, sir. Now it is visible.
Yeah.
Voice also audible.
Okay, man. So here is aluminum, which is lightweight, corrosion resistance, and the next one will be the uh, carbon fiber, which has a high strength to weight ratio. So if you compare the weight, the strength will be more in the case of carbon fiber. Okay. So again, you have magnesium alloys, which is lightweight, and again it is strong. Again, you have composites that will be customizable, and again it is durable. And you have a high strength steel, just it will be having a balance between the weight and cast. Okay. So now we'll be discussing about the design innovations. Okay. So you can see you will be having a modular battery packs for optimized weight distribution. You have advanced manufacturing techniques like 3D printing, aerodynamic shapes to reduce the drag while the vehicle is moving. And again, integration of lightweight components in chassis and body. So here, in the case of modular battery packs for optimal weight distribution, it is having a battery system that can be arranged for balance and makes the EV safer and more efficient. And again, advanced manufacturing techniques like 3D printing. Here, this allows for custom, precise, and lighter parts to be created, reducing the overall weight and it's supporting the innovative designs. And in the case of aerodynamic shapes for reduced drag, okay, here it is a streamlined vehicles bodies, just lower air resistance, so that it will be helpful in the increase in range and efficiency and safety. Okay, aerodynamic shapes not only play a crucial role in the reducing the drag, it also plays a higher role in the case of reducing the accidents also when the vehicle is at the high speed. Okay, one of the aerodynamic failure vehicle is your Tata Sumo vehicle, which is having more accidents because of the poor aerodynamic design. Okay. And here you can see the integration of lightweight components in chassis and body. So it just reduces the weight in the structure, and this is crucial for performance efficiency and increase the ranges in the use. If you see all these design innovations using this combined approaches allows the automakers to design vehicles that are lighter, more efficient, and better performing, which are essential goals in the development of EVs and next generation mobility solutions. Okay. So now we will be seeing about the global trends in the EV. So first one, increasing the use of recycled and bio-based materials. Here, the EV manufacturers are adapting the recycled plastics, metals, and plant-based materials in their design to reduce the environmental impact and also resource depletion. Okay. So the next one, if you see the global trends, the collaboration between the automakers and material scientists. Okay. Here the partnerships are being formed to discover lighter, stronger, and more eco-friendly materials that enhance EV performance and safety. The next one, the regional adoption of the specific materials. Here, you see the example, carbon fibers are most available in the case of Europe. Different regions prefer different distinct materials based on regulations, technology, and readiness, and market needs. It will be varies. Okay. So Europe is finding investing in carbon fiber for lighter, more efficient for EVs. So next one, your global trends on EV will be focusing on life cycle emissions and recyclability. So EV makers now they look beyond the tailpipe emissions, okay, aiming to lower the carbon footprint from material sources to end of life recycling and again making sustainability a key part of the entire life cycle. So the recycling plays a vital. So now we see about some case studies in the EVs about the lightweight materials. Here, Tesla incorporates the lightweight aluminum and composites in its vehicle structure to reduce the weight and to enhance the efficiency and extend the driving. And if you see the other company, the BMW. Here, the BMW i3, particularly i3, it features advanced carbon fiber reinforced polymer body, making it extremely light. But you cannot tell it is not strong. It is strong yet, and it is an industrial leading feat in the sustainable EV design. Okay, BMW i3. Although just Ford, you can see Ford F-150, it serves an example of how using a high-strength aluminum can dramatically reduce the vehicle weight. Okay, a practice now influencing the electric truck design as a well design. Okay, so the Ford F-150 is having a very high-strength aluminum that with a drastically reduced weight. Okay. And again, new companies and startups with plant-based biocomposite materials, they are doing research to further reduce the emissions, improve the recyclability, and increase the sustainability of EVs. Okay. These case studies demonstrate how both established automakers and innovative startups are adapting advanced materials and manufacturing techniques to make EVs lighter, stronger, and more eco-friendly. So now we will be seeing the challenges and future directions in the case of balancing cost and performance. Here, achieving the optimal mix of affordability and high performance with the advanced materials is a major hurdle for EVs. Okay, as new technologies often it has an increased cost. The next one will be the scaling production of advanced materials. Moving from laboratory innovations to mass productions remains difficult, especially with cutting-edge materials needed for lightweight and also efficient EVs. So the next one, ensuring the recyclability and end-of-life solutions. As material complexity increases, so does the challenge of making sure EV components can be reused or recycled responsibly. You have to recycle once the vehicles and reach the end of their life cycle. So that is the ideology of the recycling. So the last one will be the continuous research into nanomaterials and hybrids. Here, the ongoing R&D, okay, into next generation materials such as hybrid composites, nanomaterials, it is will be very essential to overcome current technological and environmental limitations. Okay, just if you are overcoming all these challenges, it's required a balance of innovation, sustainable practice, collaboration, and cost effectiveness to ensure the future growth of the EV sector. So, why you have to integrate renewable energy in the case of the your EV sector? Here, you can see why you have to integrate the case. You can see in this case of this Venn diagram. You have the different type. First one, reduce the dependency on the fossil fuels. Next one, ensure clean energy for EV charging. Next is like enhance grid resilience and reliability. Next one, support global decarbonization. So here, if you see, so reducing the dependence on fossil fuels, the clean energy and EV adoption helps lower reliance on oil, again gas, coal. Just it can move towards the sustainable mobility. Next one, powering the EVs with the renewable sources ensures that their overall environmental impact will be minimized. And again, integrating renewables and EV infrastructure makes the electric grid stronger and able to adapt to shocks and new demands. So, the clean energy and EVs are vital for achieving support carbon reduction and also climate targets. And this clean energy and EV integration not only reduce emissions but also improve energy security, system reliability, and align with the global climate objective. So, what may be the possible resources which are available for EVs, for renewable energy? Okay, it is solar. Utilize solar panels to generate electricity, which can power solar EV charging stations and reduce dependency on the grid. So the next one will be the wind energy. It involves both offshore and onshore wind farms that feed renewable electricity into the grid, supporting the large-scale integration for EV charging. Next one will be the hydropower. It provides a clean, steady, and reliable sources of energy, making it ideal for consistent EV charging requirements. Again, you have a biogas. It acts as a supplementary renewable source, converting organic waste into usable energy for EVs or the wider energy. Okay. So these diverse renewable energy sources not only enables cleaner EV charging, but also advances the overall sustainability of the transportation system. So you can see the global examples in the case of EVs. Netherlands, sorry, you have a solar power EV charging stations. The case of California, okay, USA, you have a vehicle to grid pilots with renewable energy. Okay, so here you can see Netherlands is pioneering the use of solar energy for public and private EV charging infrastructure so that it reduces the grid dependence and emissions. The case of California is leading into vehicle to grid projects where EVs not only charge from renewable source but can also supply stored energy back to the grid, increasing the grid flexibility and resilience. China, they are large scale and solar power EV grids they have. Okay, with that solar power. China is deploying most networks where wind and solar energy directly powered EV charging stations, supporting rapid EV adoption and also cutting the emissions. Again, India, here just EV is integrated with the solar microgrids. India is just implementing microgrids powered by solar energy to facilitate EV charging, especially in the areas with limited grid connectivity, advancing the rural electrification and clean mobility. So these real world examples from different continents show how nations are combining renewables and advanced technology to make EV adaptation just possible. Okay. So next, what we are going to do, the case of the most thing, the implementing the renewable energy sources for EVs. What is the problem we have? Higher initial cost, intermittent renewable energy supply, and again infrastructure gaps. So what are the solutions we can do? The battery storage systems, whenever the more renewable energy available, you can store it by observing that policy incentives and subsidies and public-private partnerships. So these are the solutions which we have. So where we are traveling for the future directions. The case of EV. First one, expanding the renewable energy powered EV networks. The growth of EV infrastructure will increasingly reliable on renewable sources like solar, wind, and hydropower to provide sustainable charging options nationwide and globally. The next one, enhancing energy storage technologies. This is the most important future direction. Here, advances the battery and storage system will be crucial for the managing the intermittent nature of renewables. Okay, because it's not continuously supplying, so that the storage technologies will ensure reliable power or EV at all times. Sorry. So, developing the global standards for integration, creating a universal standards for interoperability, grid connection, and charging protocols will help streamline the worldwide adoption and scalability of renewable powered EVs. So the next one will be the promoting community-based renewable EV solutions. So localized strategies such as charging infrastructures will encourage broader participation and equitable access to clean mobility solutions. So the future of EV depends upon the wider deployment of renewables, advanced energy storage, international cooperations, and local initiatives to create a sustainable and inclusive transportation ecosystems. So the breakthroughs in the case of EV motors, you can see the advanced algorithm, new mathematical computational methods are making the EV controllers more efficient, responsive, and able to optimize energy consumption in real time. Okay, the silicon carbide technology. Okay, here the silicon carbide based components perform better than the traditional silicon in the power electronics. So it allows for higher efficiency, reduced losses, and more compact and lightweight controller designs. Integrated power electronics. Here the integration of various power electronics such as inverters and converters just into unified modules streamlines the design so that it boosts reliability and reduces the manufacturing complexity in the EVs. So the AI integration here, AI is now being used for predictive control, diagnostics, and adapting to driver behavior, leading to smarter and safer vehicle operation. So these breakthroughs collectively enhance the performance, efficiency, intelligence, and reliability of modern electric vehicles, paving the way for more advanced and capable EV systems. So here the motors basically converts electrical energy to the mechanical energy. The controllers, it manage motor speed, torque, and efficiency, and issues smooth acceleration and regenerative braking, and it optimizes the energy consumption. So you can see the breakthroughs in the case of your EV motors. Okay, the permanent magnet motors, axial flux motors, switch reluctance motors, and high speed motors. These motors, it is you can see these motors just represents the cutting edge innovations driving the improved efficiency, performance, and again compactness in the modern electric vehicles. Okay, So you can see the global examples. The case of this EV controllers. Okay, so you can see this breakthroughs, advanced algorithm. We have just seen about this, and this you can see the global examples. Tesla. Here you can see the advanced magnet motors, which are high efficiency and having a high power density. And Rimac Automobile, it pioneers in high performance axial flow motors, enabling just compact yet powerful electric supercars with world class acceleration and efficiency. Okay, Rimac Automobile. Toyota, it focuses on innovative integration of motors and controllers within their hybrid vehicles, optimizing the performance and energy management for both electric and hybrid drive modes. BYD, Beyond Your Dreams. This develops cost-effective motors using rare yet free designs, helping reduce levels of scarce minerals and lowering production cost while maintaining the good performance. So these examples how the EV industry is advancing motor technology through a mix of efficiency, innovative engineering, and sustainable material strategies, driving the global products. Okay. So what are the future you can see the challenges? Dependence on rare materials for the manufacturing, thermal management in the high power systems. And again, what are the things is like high development costs. Solution is like we have to go for rare earth free motor technology like BYD. And again, advanced cooling system for the batteries for reducing the failures and collaborative research and development. Okay. So the future directions. So the development of fully integrated motor and control units, combining the motor and control into a single and compact unit, which can improve the efficiency, reliability, and simplify the vehicle assembly. And again, expansion of AI control system.
Sir, so
Which,
Joshua, sir.
yeah, ma'am.
So
Yeah,
sorry
ma'am.
for the interruption, sir. Sir,
Okay.
our session time is up to 7:30. So we just crossed the
I have
second.
one more slide.
So just waiting, sir. Okay, sir, no problem, sir. No problem, sir.
Yeah, yeah, just thank you. Thank you.
Okay,
I will
sir.
finish. I will finish.
Sorry, sir. No, sir. Sorry. Actually,
No
I'm
problem.
very sorry, sir.
No problem. Okay.
Okay.
So here, yeah, continuous focus on efficiency and cost reduction. Its ongoing innovations aim to make EV motors more energy efficiency whilst bringing down production and operational costs, making EVs more accessible for consumers. So exploring of superconducting motor technologies, this is research into superconducting materials could lead to ultra-efficient motors that offers highest power density and lower energy losses, revolutionizing the future EV designs. Okay, so these forward-looking trends reveals the focus on integration, smart technologies, maximizing the performance and efficiency, so that it reduce cost and adapt to the cutting-edge materials for the next wave of EV motors. So up to this, I'm just concluding this faculty development program session titled on Smart Energy Management System for Low Carbon System. I would like to extend my heartfelt gratitude to all the resource persons, participants, and organizers who made this event possible. So thank you all for the participation, for the commitments towards the learning at this after working hours. Wishing everyone a great success in their future endeavors and hoping to see you in many more such academic engagements. Thank you.